Welcome everyone to the first afternoon track that's going on here at the Embedded Vision Summit. I'm here to introduce Simon Morris, our next speaker. Simon has over 20 years of experience in both the private and public semiconductor companies. He's responsible for leading CogniVue's evolution, I should say, from an R&D cost center through the spin-out to an independent, privately held fabless semiconductor and embedded software business. Prior to joining CogniVue, Simon was director of BDC Venture Capital. From 1995 until 2006, he held a variety of senior and executive leadership positions at Sana Semiconductor and senior positions at Texas Instruments as well. Simon has a master's in engineering and a bachelor's in electrical engineering from the Royal Military College of Canada, and is a member of the Professional Engineers of Ontario, and advocating tonight's game, Canada versus, Tampa Bay they're playing tonight, Simon? Exactly, yeah. Who would have thought Tampa Bay? I mean, that's in Florida, right? They play ice hockey? I live in Tahoe, we play ice hockey. The kids go down the street. Please join me in welcoming Simon to the...
Okay, good afternoon, ladies and gentlemen. I'm here to talk to you a little bit about what is turning into a real battle in the automotive world, and that's the battle for ADAS. So I'm going to outline some of the trends, challenges, and opportunities in particular vision-based ADAS for autonomous driving. Okay, number one, why ADAS? Well, basically, automotive driver assistance. It saves lives, and if you look at the number of traffic fatalities a year, there's 3,500 or 1.2 million people are killed each year. That's a lot, and that plays on the minds of the buyers, the people who buy vehicles themselves. When you're actually going out to look at a vehicle, if it's got additional safety features in it that can save yourself or your wife or your spouse, your children, you're likely to veer towards buying that car over the car that doesn't have those safety features. Then the other thing that's coming up, of course, with autonomous driving or semi-autonomous driving is the attraction of actually taking your mind off of driving and having the car drive yourself. Now, we're ways off from that, but when that does come around, the average driver in the U.S. spends at least an hour commuting, not including, of course, driving to do errands and chores or whatever else, or taking kids to soccer or hockey practices, but 1 hour driving to work and back. So that's giving time back to the driver if we can eventually get to a car that can be a semi or autonomous. So what is vision-based ADAS? Well, it's basically things like lane departure warning, collision avoidance to brake the vehicle when you're getting too close, or warn the driver when you're getting too close to an object in front of the vehicle. Lane departure warning to warn, or notify the driver when he's changing lanes or she's changing lanes and shouldn't be. Blind spot detection for, again, changing lanes, and as well as pedestrian detection and traffic sign detection. Those are some of the vision-based applications that are being enabled today. So that's vision in automotive. The other thing is why vision in particular? Because, of course, there's other sensor technologies out there that can provide these safety features, and they've seen radar and LiDAR in particular being used for collision avoidance. There are being some tests more recently for autonomous emergency braking with comparing these different technologies, and in terms of the ability to brake the soonest and quickest. And of all the technologies, vision-based, or in this case, stereo camera, actually had the best performance in recent testing done by Thatcham Research in 2013. So the trends, well, as I said before, fear is actually what sells cars, and besides, of course, how the car looks and the color it is. The safety features, everything from a rear camera to a forward-facing collision avoidance, are features that consumers really want to have. The other thing that's, of course, driving the adoption of vision-based ADAS is the introduction of safety ratings and safety standards, new safety standards from NHTSA and NCAP in particular. In general, ADAS is actually the fastest growing segment in the automotive electronics market. If I remember correctly, something like about 20% combined aggregate growth rate over the next 5 years. And it's not just appearing in high-end cars. Everybody always thought of forward-facing cameras only appearing in high-end cars, but now you're seeing it in entry-level vehicles as well. Some examples there like the Hyundai Sonata, the VW Touran, Toyota Auris. So it's coming. It's not just appearing in the high-end vehicles today, but also just the everyday vehicle that consumers buy, and it's becoming a standard feature. So what makes ADAS vision in particular so challenging? Well, there are 4 major things. One is high data processing, and this data processing requirement is growing as the complexity increases as well. Data processing means the movement of pixel data in particular on the chip inside the camera. Huge computational load. Of course, more and more things are being added to the processor. We'll talk about this a bit more later. So huge computational load. And it's always on, so the camera, of course, is consuming power and therefore generating heat. So one of the challenges in any sort of confined camera design is going to be power dissipation. And then, of course, it has to be designed to be safe and reliable, and that can't be understated. It's particularly like a design know-how that takes a while to build up. It's not something you instantly decide, oh, I'm going to design this chip for safety. It's something you got to learn about when you're designing your processor core IP, and as well as your software and the chip itself or the camera. So let's look at the data processing demands first. Over the next few years, you'll see really 4 times growth in input pixel data bandwidth. So going from 30 megabytes per second of pixel data coming into the processor core inside the chip to 120 megabytes. This would be going to stereo HD as a common camera configuration in cars. And then a 10x growth actually in data processing demand as a result of, that's within the processor core inside the chip, of around 1.2 gigabytes per second. And this comes from, even though you've got 120 megabytes of data coming in, you've actually got a lot more data moving around inside the core. And that's really the huge problem. And it comes from, of course, the processing of a megapixel HD video, but also the building of image pyramids for classification that's typically done. That's 5 times the image or frame size typically that's required. The storing of intermediate results in the processing of these algorithms on the core, that's usually data requirement for that is somewhere in the 5 to 10x the frame size that you got to store or move around. And then, of course, you're running multiple applications. So a safety camera, an automotive camera would be potentially running half a dozen to a dozen different type of feature detectors and maybe up to half a dozen different types of classifiers. So the other thing, of course, there's this huge amount of data movement that's going on, and it's growing all the time within the chip. In addition to that, you got this huge computational load as well. And of course, with safety, you need high accuracy. High accuracy means usually higher computational requirements. And in the combination with that, you've got all these safety critical applications running at the same time. So you've got, for instance, pedestrian detection running with autonomous emergency braking, collision avoidance, cruise control, lane keep assist, and so on. All these things are being done at the same time. And then, in addition to that, of course, the algorithms that are running, you'll have proprietary-based versions of these algorithms running, or handcrafted versions. And then, more recently, there's a lot of hype, I would call it, around the introduction of CNN for classification, and the emergence of, in general, deep learning type algorithms for classification in future automotive cameras. So overall, you have a computational loading somewhere in the ballpark of about a teraflop, which is in the supercomputing category. So the other part of the problem is, of course, the power consumption. You've got this huge supercomputing level of processing that's going on inside these chips in the cameras, and yet you have really a small amount of space to get that heat out that comes from the result of the power consumed by these processors. So as an example, a forward-facing camera here, this is an example of Continentals. it has to, of course, you can't have a large area. It can't take up a large area in your windshield. So you've got a small confined area in which you can put your chips. And it's sitting in the sun on the windshield, so of course it's baking. The typical requirement, let's say, this is a sort of an average. You got to get all that thermal heat out. You got to hit grade 1 type automotive qual, which is minus 40 to 125 degrees Celsius for the chips that are inside there. Plus, you're really trying to do this in a power budget based on the thermal dissipation of the module itself, somewhere in the 5-watt range. So you got to have this high performance processing done in this small power envelope. If you look at an high performance Intel processor, an NVIDIA processor, you really have to get about 100 to 200 times more performance than what those processors can currently offer in order to meet the processing demand in that power budget. So safety and reliability, this is also critical. There's no room for error in safety critical applications. You can't, for instance, brake the car if there is no person in front of the vehicle. That's also a hazard. You not only have to brake the vehicle when there is a person there, but you don't want to brake the vehicle when there is nobody there. And of course, it has to work 100% of the time. And if for some reason it fails, you have to also be able to detect the situation when it fails, and warn the driver or warn somehow bring that to the attention of the driver that the system is not operational. And then, of course, the actual standard that pertains here in terms of functional safety, ISO 26262, which is about 12 huge encyclopedias of safety requirements, designed for safety requirements, affects all parts of not only the design of the camera itself by the tier 1 that's delivering the camera to the OEM, but the chips inside that camera, and then the IP vendors, both software and hardware IP vendors that deliver it to the chip vendors. It can't be an afterthought. You have to actually take these things into consideration before you deliver that IP. So the opportunity, the opportunity, of course, is the market size. There's, by 2020, according to the ABI research, somewhere around 200 million cameras will be in cars. And ADAS itself is the fastest growing segment, as I mentioned before, in the automotive electronics market, with about 20% growth rate between 2014 and 2018. And then vision processing challenge, of course, will bring, in particular, because this is a huge problem, getting this high performance vision processing accurate and safe into the market at low power, has created, of course, the emergence of some new players who can deliver on that requirement. In particular, Mobileye, that has a head start on everybody. Their revenue is somewhere in the 140 million range, or it's probably beyond that now, maybe closer to 200 million. And they have a market cap over 10 billion. And I think they're still losing money, but nevertheless, there's huge potential there. And they have the lion's share of the vision ADAS market today. And of course, our company, who is enabling the competition to Mobileye. So Mobileye has 80% of that market today. It's a turnkey black box solution. And the tier 1 combatants, the companies that are competing against Mobileye, the big tier 1 companies are building camera-based ADAS systems that are better than Mobileye's, like Bosch, for instance. They have a major investment, of course, in the development of the applications. There's an optimized vision libraries that need to be delivered, extensive video test databases that have to be developed, and there are, of course, new system-on-chip processors that are appearing in the market to do battle. So Freescale's recent announcement of their S32V, which is a competing chip to the Mobileye IQ2. And then, of course, the introduction of specialized programmable vision processor cores, not only Apex, which is what CogniVue's developed, but other companies like Cadence with their IVP-EP and CEVA with their latest VM4. So the winners in ADAS will be strongly positioned basically to win in this, not only this ADAS market, of course, but if they win here, they're well positioned to win in the emergence of the autonomous vehicle market in 5+ years. So in summary, the future of ADAS and autonomous driving rests really on advances in embedded vision processing. So it's how do we actually deliver this high performance, ever increasing requirement for vision processing at a low power number and do that cost effectively. And of course, what's going on right now is a battle for market share. You got the company with the lion's share today, Mobileye, at 80%, and you've got the big tier ones coming in and, of course, chipping away at that market share. And that's I guess, for investors at least, so the ones who speculate on the market, an interesting battle. High performance, low power embedded vision cores, of course, are going to play a critical role in solving the problem and helping with that battle in sort of arming the semiconductor companies and in particular the automotive companies that use the chips from those companies. We have, of course, at our table some demonstrations of some of that vision technology if you're interested in taking a look. And that's my presentation. If you have any questions, I'm more than happy to answer them.
Hi, you mentioned tier one suppliers. How close are they to catching up or launching their own product that competes with Mobileye?
Well, some of those that I showed you are already in the market. I mean, it's not public. It's public information. Bosch, for instance, has their systems in production with Volkswagen for autonomous emergency braking. So these tier ones have systems today already that are chipping away at that market share.
So what are some of the limitations of existing solution? Is there any problems which you have identified by which you could distinguish your technology? That's number one question. Number two is, what do you think about how is vision good for long range obstacle detection, not for just pedestrian detection at a short range, but much more long range?
Okay, I'll answer your second question first. So, I mean, vision is dependent on the resolution of the camera and how far away, how far away you can see is based on the number of pixels that you need for your classifier or detector, and that's based on the resolution of the camera. And so, of course, you eventually want to see farther than you can see today. You always want to see something further out, and that requires higher resolution sensors to be installed in these cameras so they can see farther. So we'll continue to, I'm sure as we progress, you'll go beyond HD stereo to 4K stereo in order to see farther or classify better.
Can you explain?
Oh, sorry, I didn't answer your first question though.
How do you differentiate from existing solutions?
Ourselves or Mobileye? Or well, we focus on, in our architecture, we tackled the problem of data movement. And that, I showed that in the slides essentially. I didn't say specifically that we were doing that, but if you see, the problem isn't necessarily performance as much as it is how you actually deal with it, all that data moving inside the core, and how you efficiently place that data, pipeline your algorithm so that you end up with a power efficient implementation at the algorithm level. And that's how you end up with a power efficient implementation. So focusing on in your architecture on data movement is number one. Everybody can build a massively parallel SIMD processor or vector processor to get the performance. So some of those things are relatively easy to address, and if you look at the different processor architectures, there's lots of similarities. They all do some combination of scalar and vector, and they all use some sort of combination of highly parallelized massive vector processing. The key, though, is data movement. If you can do that in a smart way, let's say a innovative way, you can substantially reduce the power consumption at the algorithm level or at the system level.
Can you explain a little bit in more detail about the system software and like the hardware, the software, what OS do you support? And is it like you license the actual IP or you actually make the chip, just the business model?
Well, our company?
Yeah.
Well, we license the processor core that goes to the chip companies. And as far as the OS that runs on the chip, we're agnostic. I mean, it's really irrelevant what OS is playing. The SDK that we provide is drivers for the hardware blocks in the processor core, and they can be ported to any OS regardless. We have it running on Linux, Nucleus, Integrity from Green Hills, and so on.
So what different, is it like custom applications or hard-coded in the FPGA or the processor? What does it like?
The applications are all programmable. So okay. In the automotive world, the tier ones have invested, the big tier ones have invested years of development, just as Mobileye has, in proprietary algorithms to stand out from each other. So you have to, whatever platform they're going to adopt, it's going to be something which allows them to leverage that IP they've developed. And so it needs to be programmable in some capacity, or in the case of FPGAs, it has to be programmable at that level.
I have a little bit unrelated question, but still kind of connected to your presentation. So assuming, looking ahead the road, when you accomplish your goals, you're going to have a lot of signals in your car, like lane departure, forward collision, recognition of signs and lights, recognition of pedestrians. How are you going to unload it on a poor driver? I mean, what is your strategy for handling cognitive load here?
Well, in most cases, if it's an active system, it will actually do it for the driver, so it will brake the vehicle. A passive system will, of course, just provide a warning to the driver, and then the driver has to decide what to do. But what, of course, you're seeing more and more now is an active system, so it will, like emergency braking, autonomous emergency braking, it will brake the vehicle for the driver. The driver doesn't have to do anything.
How far are we away from self-driving aircraft and drones?
Self-driving aircraft?
Yes.
I don't know.
Is this something that this kind of technology is going to be applied to?
Well, I think anything that's moving, that's smart in some way, robotics, cars, airplanes, will need very high performance vision processing technology to do so, just to navigate, to move around. And ideally also be able to decide what to do when it's up in front of something. So the technology that's being used in cars maybe will eventually be used in UAVs and drones, and they may be one day in aircraft, but I think we're a ways off from there. They're not even in cars yet. I mean, you see demonstrations, but you're probably 10 years away from seeing autonomous vehicles, at least 5+. Truly autonomous.
Any others?
Hi, just one question about programmability of the core. So you mentioned before the Intel core or the NVIDIA core, which I guess are relatively straightforward or more easy to program. So SIMD cores are more difficult to program. What's your approach to get that easier for the programmer?
Right. Well, table stakes is programming in C. Everybody has to have a compiler of some form. What we've done, in particular, to deal with the programming of data movement. So there's massive SIMD programming, and that you can handle by developing a C compiler with vector extensions. But then, and that part of programming is actually relatively straightforward. It's really programming to get an efficiently pipelined implementation on the processor. That's the challenge. In our case, to deal with the data movement problem, we developed a system-level tool we call the Apex Core Framework, which is analogous to, say, MATLAB Simulink. Bad analogy, but it's something like that. And it allows you to pipeline the data movement and the kernels to make up your algorithms so you can end up with an efficient implementation relatively quickly without having to go in and understand the guts of the processor to the way we do.
So in terms of standards or regulations for self-driving cars, is there anything like that? Aspiring companies aspiring to produce a self-driving car, do they have to meet certain constraints besides what we know it's common sense? I'm talking legal.
Yeah, I don't think I can answer that question for you. I mean, there's safety standards today for lane departure warning, blind spot detection, collision avoidance, pedestrian. These standards exist. For autonomous vehicle driving, I don't think there is anything at the moment. The legal issue is a bigger one. Who's responsible when the autonomous vehicle crashes? That's something I think the business and legal experts have to work out over the next decade.
No lawyers in the room, huh? Well, Simon, thanks for sharing that with us.
You're welcome.